Thank you. And good morning, good afternoon, good evening to everyone. What we're going to cover today touches on 4 topics, hopefully of relevant interest to you. We're going to talk a little bit about sensor fusion and overview of sensor fusion and how it applies to your development process. Going to talk a little bit about ADAS development and WorldSim and how that technology can help you accelerate your ADAS development. Touch on hill integration and how the hardware in the loop is becoming a really important factor as we start simulating a lot of these worlds to accelerate our development process. And then we're going to touch on a use case on integrating a radar simulation hardware with our partner Rohde Schwarz, which is why we're doing a co-presentation here. So I'm Ian Dodds. I'm the North American Technical Director for VI-grade. I'm also the product owner for WorldSim, which is our visualization engine. VI-grade builds real-time driving simulators, and we simulate everything about the world, the vehicle physics, the audio, the visuals, the sensors, in real time to give a complete immersive experience. And Ram, I'll let you introduce yourself as well here.
Sure thing. Thanks, Ian. Hello, everyone. This is Ram Mirwani. I lead the business development effort for Rohde Schwarz for North America, focusing on automotive. And today I'll be sharing some comments on how our radar simulators are enabling simulation-based testing for ADAS functions together with Ian.
Okay, so let's touch a little bit about what is sensor fusion. So sensor fusion is the combining of multiple sensors to improve your perception accuracy. Sensors are used in the vehicle to perceive the world. I can detect vehicles, obstacles, pedestrians, road sign detections, but one sensor is not necessarily enough to validate that what the sensor is seeing is really what it's seeing. So it's the combination of using camera, radar, LiDAR, and ultrasonics to basically reduce the uncertainty and enhance the detection and improve the decision-making process of your detection algorithms. So it's the blending of multiple sensors, getting the opinion of each sensor into one combined algorithm that says, yes, that is a car in front of me. Yes, that is a road sign and it's a stop sign. So that's really the problem we're trying to solve with sensor fusion. What are the challenges in sensor fusion? Well, we do get a lot of false positives, and as I'll show you in the subsequent slides and examples, it can be very difficult to actually positively identify that what a sensor is picking up is what you really think it is. And the worst case scenario is it picks up something that isn't really what it's supposed to be and you make a wrong decision. The synchronization, because we're using multiple sensors, the synchronization and calibration across multiple sensors are very important. They all need to be in sync, producing signals that are time synced and at the same time, so that when we're analyzing the frame coming from each sensor, we can actually truly detect what is being done at that time step so that we can make the right decision. Obviously, some of these algorithms require a lot of machine learning, AI type capabilities. So there is a high computational requirement put onto that, and in order to do that in real time, to make a real time decision, becomes a challenge. And onboard compute becomes very, very, very important. And then there's also edge cases when we're simulating ADAS capabilities. 90% of what you see can be predicted. It's the 10% at the top end that is very difficult to reproduce. What happens if the dog jumps out from behind the car 10 seconds later or 5 seconds later and you don't have that time to react? These edge cases need to be simulated and accommodated within your algorithms. So these are some of the challenges that we're facing, and simulation can help solve a lot of this to validate it before we get to the real world where things can become very expensive and potentially dangerous to validate. Let me walk through a couple of examples here of sensor fusion. And all of this can be simulated as well. So we take, 4 typical sensor outputs: a long-range radar, a short-range radar, your LiDAR output, and your vision sensor. And they come together, and then we can take in other characteristics of the vehicle, whether the vehicle position, the vehicle speed, possibly accelerations or compass directions, and those are combined together in a fusion algorithm that can then be passed on to your perception and planning algorithms to decide, do I apply the brakes? Do I steer the vehicle? So fusing these together through those algorithms. Of why it's difficult to identify what's going on in a scene. Over here on the left, I have a typical simulated driving scene. We're driving down a road here in Wolfsburg, and we have two vehicles identified, or two vehicles I can see as a human. But a sensor needs to be able to pick up these two vehicles so I can then make a decision of what I'm going to do in my next step on the driving. Obviously, with a camera sensor, I can then take detection algorithms and say, okay, here is a vehicle. And if you've seen some of these, and I did a presentation on perception last month or a couple months ago, we're about the 70–80% confidence level that these algorithms can pick up a vehicle and say, yeah, that's a vehicle. But if I didn't have a camera sensor and relying on the radar can pick up a lot of other information within the scene. Radar's bouncing off of anything out there, road signs, garbage cans, that type of thing. And really what I need to do, I need to be able to pick out these two dots within the radar signal to say these are the two vehicles I'm interested in, so I can actually compute possibly their distance from my vehicle. Again, LiDAR is a very powerful tool, but it produces very large point clouds that can return everything from the tree structures, building structures. And what I want to do is I want to pick out these two vehicles within the scene so that I can then reduce that point cloud down to an area which I can then compute and assess. Segmentation, again, we can actually have algorithms that segment a camera image and pick out distinct objects within the scene. But what I want to do is I want to pick out these two vehicles and ultimately all the vehicles in the scene within the sensor. An example of how to reduce data is if you take the camera scene and I do an object detection, so I know roughly where the object is here, and I validated that with my radar sensor, my LiDAR sensor, and I said, yep, those are vehicles. And then I get this massive, 100,000 point cloud back of what's going on in the scene. But I can combine these two sensors to reduce that point cloud down to an area of interest of which I can then assess and get a much quicker answer because I know this is the area of interest where the vehicle resides. So where does simulation fit within ADAS development? Like I said earlier, simulation provides a safe and controlled and reliable testing conditions. I'm not out there putting anyone at harm. I'm simulating very dangerous conditions, dogs jumping out from behind vehicles, pedestrians, other vehicles, where we don't actually damage property or individuals, and we can actually iterate on large numbers of scenarios without causing any harm. Obviously, we can do this at great speed. So it does accelerate your validation process. You can go through many iterations with many variations within simulation. It allows you to test edge cases. How does my algorithm perform at night? How does it perform in fog? How does it perform with one pedestrian? How does it perform with 10 pedestrians? And then we also integrate that with our tool set like VI-WorldSim, which is a very realistic world sim environment. And the more realism we get into the world, the better answers we get from our simulation, and so on and so forth. Some of the ADAS use cases that have been proven out through simulation, and we've got examples of this in our sim center to demonstrate to you if you're interested in paying us a visit. Automatic emergency braking, applying the brakes if you're getting too close to the vehicle in front. Adaptive cruise control, controlling the speed of the vehicle based on the surrounding conditions. Lane keep assist, keeping the vehicle within the lane. Blind spot detection, traffic sign recognition, giving haptic feedback to the user based on what's happening around the vehicle based on the sensors in the vehicle. And then we can also do things like obstacle detection and pedestrian tracking, and the obstacle detection can be endless. Piles of rubble, construction material. You think about it, in the world that's out there, we've got to be able to simulate all of that in order to truly address the ADAS edge cases. So let me introduce you to VI-WorldSim. VI-WorldSim is sort of the visual engine that sits in front of the simulator, and it's a lot more than just that. It is a high fidelity graphics engine that can be easily interfaced offline and online into your ADAS development. We provide a very powerful API, which is in Python, C++, ROS, as well as MATLAB Simulink, so you can actually interface with your control algorithms and development algorithms from the visual scene. We have a very powerful traffic engine, which allows for AI traffic, which gives the traffic, pedestrians, animals within the scene a mind of their own. And we can give them predefined routes to take, definitive actions to be taken when a vehicle passes through a certain zone within the scene. We also simulate a lot of the sensors that are used within the vehicle, as well as underlying ground truth for validation. So we simulate camera, LiDAR, radar, ultrasonics. And it's driver simulation based. So driver in the loop is one of our key product strengths. Not only can we simulate offline, but I can put you in front of a steering wheel and you can drive that scenario within the WorldSim world. And then we also offer a large variety of pre-configured scenes and scenarios for you to run your testing in. We run in real time. It's very scalable. We can scale up so that we can, based on the number of sensors you want to simulate, the number of visual nodes you want to simulate, it's very scalable. We have a very customizable API. The worlds can be customized, and we follow standards integrations, and we have a very large content library. So in order to simulate ADAS, you really need, I've always said you need three things. One is content. You need worlds to drive in. You need vehicles to place in the scene that cover a vast majority of the vehicles you see in the real world. You need obstacles. You need the ability to create new content so that you've always got updated environments in order to validate your edge cases on. On top of content, you need behavior, whether it's weather conditions, triggering events, having traffic simulate as if it was real world traffic, and the ability to co-simulate with other tools if there's things that are missing within the tool set that you want to simulate in a more advanced manner. Be able to do time step locks co-simulation with other tools or hardware. And then you also need to simulate sensors. You need to simulate all the sensors available with the camera and provide a real-time sensor feed, any format that's very similar to what would come off of a real sensor, whether it's a CAN bus message or a point cloud. We need to build simulators, and WorldSim can simulate all of this. WorldSim has the content, the behavior, and the sensors available within the tool suite. WorldSim is more than just a graphics engine that sits in front of a simulator. That is the traditional use case. But as we expand where WorldSim fits within your process, we have the sensor simulation for ADAS, so we can give you step-by-step sensor feeds that feed into your algorithms. We have a tool creation process that's constantly expanding that gives you a very intuitive way of creating new environments, new scenarios, and gives you a constant feed of environmental updates. WorldSim can also be integrated for hill use, camera in the loop, radar simulation, camera injection, taking the signal outputs and feeding that to a hardware component, which could be the hardware that you're selecting for your vehicle, or you could be using it to measure latency or some aspect of performance of the physical sensor. We can bring in the hardware loop in the loop component. WorldSim can also be used for integration, where I want to integrate it into some third-party simulator or some third-party process. It can be used as a graphics engine to drive that. It doesn't have to be in front of one of VI-grade simulators if that's not necessary. And WorldSim can also be implemented within the cloud for data management. As you can imagine, we make a lot of data out of these simulations, and having some sort of data management and cloud simulation for large DOE type studies is a very useful tool within this world. So there are multiple uses for WorldSim and multiple ways it fits into your business process. One of the things that like I said earlier, we need content. So we offer a large library of tracks, roads, and conditions. We have about 13 miles of downtown Chicago. We have some, 160 plus different areas of the world that are mapped out. All the roads are GPS accurate. They're material accurate. You can drive them in real time. Real time for us is 120 frames per second. But we have a large content, digital twins of the world that you can actually implement and use within your simulation. So content is something that the WorldSim has, an abundance of. The content can be very realistic. Here's an example of WorldSim versus Google Maps. I took, the street view of the Google map. As you can see here, it's a very, down to signage position, tree position, garbage can position. The only thing I think I says doesn't change in the simulation, but could if you wanted it to, was the gas price on the gas station. But as you can see, they're very, very realistic renderings of the world and very accurate representation, digital twins of real world conditions. We also have our own AI traffic engine. You can interface with other traffic engines like Sumo if you needed to. Where the vehicles can behave and are defined behavior based on AI characteristics. You can have someone driving very aggressively, someone driving very slow, and they all independently and deterministically drive this scenario so that it's very repeatable as you execute the simulation. This example of a roundabout situation where the vehicles are all behaving themselves and playing nicely within the roundabout. WorldSim also offers sensors. We have camera sensors, radar sensors, LiDAR sensors, all virtually simulated within the simulation. We also offer what we call our virtual camera. Because we control the simulation, I can tell you all the aspects of where the items are within the simulation. So for instance, if you're writing an algorithm where I want to validate the detection of a vehicle, not only can I provide the camera feed to go into an AI perception algorithm to look for the vehicle within the scene, but I can also tell you, yes, that is the vehicle that was rendered within the scene because the virtual camera is the ground truth of that simulation. So by combining all of these sensors together, you get a very rich environment for developing your ADAS algorithm. Let me touch a little bit on hardware in the loop, because ultimately, once you've developed your ADAS algorithm virtually, you want to start bringing in hardware components and making it more realistic. And these are hardware in the loop components that we've integrated with our VI-grade technology stack over the years. And I start a little bit over here, more on the physical domain with the vehicle dynamics, and then we move more into the sensor domain over here on the right-hand side. So we have examples of bringing brakes into the simulation, where I can actually have a real brake hardware in the loop component, where the simulation would then send out a signal to the brake hardware component to say apply the brakes, and that would then apply some physical hardware where the brakes are actually applied to a physical rotor, and then the properties of that are fed back into the simulation. We can also do that with steering. We have examples of that. We can also do that with dampers. So if you want to evaluate the integration of a physical damper with your vehicle physics, that can be done with hardware in the loop. As we move into ECUs, we can also simulate in real time a lot of the vehicle protocols, such as CAN bus, automotive Ethernet, and such like. So we can feed data to an ECU in order for it to take its decision and provide input back to the simulation. So we've actually got examples of developing ECU algorithms within the context of plugging it into a virtual simulator. Camera in the loop. As you're evaluating cameras, we can actually point cameras at a WorldSim screen and have that camera perceive and operate as if it was looking at a real world, although it's really just looking at a screen. We can do ultrasonic simulation, hardware loop, where we actually have physical ultrasonic sensors within the loop, providing that information back to the simulation. Our partners, Rohde and Schwarz, have an example of radar simulation, where I can take physical radar sensors and produce a signal that would actually emit a radar signal to a physical sensor, and that sensor would then be included within the simulation as feedback, so we can actually evaluate the real sensor within the simulation. And camera injection, where I can actually simulate camera output from the simulation through special hardware that actually injects the camera back into an ECU or a control unit as if it was coming from a physical camera. So here's all the examples of hardware in the loop and how we could implement them with simulation. It's becoming a very, very important step within your development process when we want to actually start evaluating hardware and not just do a virtual simulation. What I want to do here is talk a little bit about what tools apply to what stages. So I made a simple use case here where you've got your basic stages I go through when I'm designing and evaluating various aspects of my design. I'm doing possibly sensor selection. I'm doing ADAS algorithm development. I'm doing hardware integration testing, and then ultimately sign off of the final solution. And this is how it applies to multiple areas, which is, I'm going to apply it to vehicle physics, to radar and radar simulation and radar selection, to vision camera selection, and to your ADAS control unit. So in the design and evaluation phase, we can actually use some virtual tools to help support this. In the vehicle physics area, I can support it with our car real time, which can give you real-time simulation on the vehicle physics. Radar simulation, we can use WorldSim to simulate that from a virtual perspective. Vision camera, we can actually use WorldSim again for that. And we can also then integrate with MATLAB and Simulink, which is part of our support suite that WorldSim and car real time also integrate with very well for some of possibly your initial ADAS development. Then I move on to I want to start selecting sensors and evaluating physical sensors potentially. And this is where we can start bringing more hardware into the loop. So I still have my vehicle physics is being simulated because I don't have a real vehicle I want to test on. But we can start bringing in the Rohde Schwarz hardware for radar simulation. We can start bringing in a physical camera in the loop or camera hardware in the loop capability integrated with WorldSim. And again, using MATLAB and Simulink to develop the control algorithm. For ADAS algorithm development, I can use the car real time and then WorldSim for the sensors and MATLAB and Simulink for the control. Again, you can see how combining different tool sets for different solutions. A lot of them are still virtual, and it can become a very powerful tool suite. Ultimately, I want to do some integration, hardware integration testing, bringing in more physical components as I get closer and closer to my final production solution. Again, we can simulate that with car physics, WorldSim and radar simulation, possibly camera injection at this point because I actually have a real ADAS controller, and then bringing in a physical ECU and replacing the MATLAB Simulink with the physical ECU hardware. But again, using these physical hardware components to drive a virtual vehicle within the car real-time space. And ultimately, you do have to go to physical hardware for final sign-off, but you're reducing the amount of physical hardware you have to commit to as you're going through your development process. I thought this was a nice chart to kind of show how you can go from a 100% virtual world to 100% physical world, going through your stages of your design process. So when it comes down to, I'm going to touch a little bit on the use case, drilling down a bit more to the radar simulation. We had a use case where we've actually demonstrated this at several trade shows and for several customers, where we've partnered with Rohde Schwarz to actually drive our technology stack and integrate the physical Rohde Schwarz hardware into the simulation. So over here, this is kind of like the architecture diagram of how it all works. And it's a very simplistic view, but it all works very well. Over here, we have our simulation stack where I have MATLAB Simulink components sitting on top, integrating with our AutoHawk capability, which is our real-time hardware, using DriveSim and our car real-time component to simulate the vehicle. All of this is managed in real time using our simulation workbench product from Concurrent Real-Time, which basically updates the simulation and drives all of the components within the simulation, keeping everything in sync, taking inputs and outputs from either a simulation component or a hardware component, and providing that input to other components like the car physics to make the determination of what the next step is going to be in the simulation. Within here, we have physical controls, the driver's steering wheel, the the brake, the accelerator, that a driver and look can interact with. And this can be anything from a desktop solution all the way up to a full-blown driving simulator that you sit in a vehicle buck on top of a moving actuators and tables. We're using VI World Sim to simulate the world, which is the physical world the driver sees in front of them, as well as providing sensor output that through our Python API, I create a standard message which I can send through a ZMQ bus or a UDP message to the Rohde Schwarz hardware. Now, the Rohde Schwarz hardware then takes that signal and converts that into a physical radar emission that's then sent down a test environment into a physical sensor. That physical sensor thinks is seeing a real radar emission or a real radar signal, of which I can then send a CAN bus signal back into our AutoHawk to provide the control loop back. And we've demonstrated automatic emergency braking and adaptive cruise control using physical Rohde Schwarz hardware with the simulated world within the VI-grade stack. Here's an example of what we did at our ZPS this year, and this is our event every year where we demonstrate a lot of our technology capabilities, and customers come and present how they are actually using our technology. And this year we presented a solution where we have our static simulator. Driver can sit in the static simulator and drive down the road here. All the button controls on the steering wheel are integrated within the hardware, so they can activate features like adaptive cruise control and automatically emergency braking. Over here we have our compute stack, and then over here we have the Rohde Schwarz hardware, where we're actually simulating the physical hardware integration with the virtual world. Very, very compact setup, but as you can see, a lot of capability and interaction can happen, and you can get a lot out of a session or a set of hardware like this. Let me just take a break here and give you an overview video of this setup in action. And then to conclude, I'm going to just show you a little bit of the output from that simulation. And what I'm showing you here is the world sim scenario that's being driven in front of the driver. This here is the simulated radar sensor of what's being seen here. Every so often you'll see a very fast object that happens to be the light post coming down the side of the road here. And we have three objects that are being detected here by the radar, which are the three vehicles in front of us. One of the things that Rohde Schwarz provided us in order to develop this was an emulation of their hardware, so we could validate the communication between WorldSim and their radar simulation hardware before we actually had their physical prototype. So we actually used virtualization of their hardware in order to develop this. And then what I'm showing over here is how the Rohde Schwarz hardware is interpreting the signals coming from WorldSim prior to emitting those signals out to the physical sensor. So if I play this again, you'll actually see that we have a one-to-one correlation of the objects being detected within WorldSim, and then how those are being emitted and generated by the Rohde Schwarz hardware over here within the Rohde Schwarz simulated software. And with that being said, I'm going to hand over to Ram to talk a little bit about Rohde Schwarz participation in this and what they offer as a product offering to support these capabilities.
Thank you, Ian. Excellent. So just a brief introduction for Rohde Schwarz. We are a German company that has been around for a very long time, since 1933. We are independent, family-owned, and main reason for that is it enables us to drive our investment in different areas. We're about 3 billion in turnover, and we have a global presence. Okay, when we think of automotive, Rohde & Schwarz offers test equipment in several different applications, as shown on this slide when it relates to automotive. And what this enables us to do is, as we work with different applications in the automotive sector, we are able to learn the test needs, the test challenges across all these different applications. And for each of these applications, we are involved for design validation as well as production test, and all the steps in between. And having this broad footprint in automotive enables us to not only deliver the test equipment for specific applications, but then also work with the automotive ecosystem to deliver the test capability for new challenges coming up and future generations of new products as well. Okay, and that's what we focus on, together with delivering the test capability for today. And so for radar testing specifically, as shown on this slide, Rohde & Schwarz has got a variety of platforms that is involved for testing radar sensors in the R&D side for research and development, new generation, but then also following that radar sensor as it gets integrated into the vehicle to deliver some of the key vehicle performances. And this is becoming more and more important as we relate to safety functions and ADAS. So over the years, as we have worked with the OEMs, we bring our radar simulation and our radar test capability to become a part of the development process for ADAS functions. And that's where this partnership with VI-grade is enabling us to not only leverage the simulation-based capabilities and test strengths that simulation environment bring to the development process, but now to be able to integrate the real-world sensors and the simulation capability together and make it a stronger part of the overall development process. And that's been the focus that we have over here. In the top right-hand corner, you'll see that Rohde & Schwarz is also involved in vehicle-in-the-loop testing, where you can have the vehicle sitting on a dyno, and now you can actually do the radar functional test for the radar sensor when it's on the vehicle, which is often the next step after you do the drive simulation test that Ian just showed, right? So we are involved in all the stages, and in this slide, we just try to share that with this broad footprint in radar testing, we are working with our partner, in this case, VI-grade, to enable next generation test capability when we're talking about ADAS functional tests as well as system and subsystem level testing. And so when we bring together the actual radar sensor and make it a part of the overall test loop, as Ian has showed, what we feel is this is the next step after you do just simulation-based testing, which definitely has a very strong place in the overall development process. And by bringing in the actual radar sensor, you now have an additional level of test capability where you can do the co-simulation with the actual hardware pieces that are involved. And this can be extended even to subsystems. For example, for emergency braking, you could also involve not just the radar system, but also the brake assembly, and make that a part of your simulation together with the drive simulation perspective. So we feel in partnering with VI-grade, we are opening the doors for the co-simulation and enabling the automotive ecosystem to have a higher degree of test capability and opening doors for safety functions to be evaluated and developed in a much quicker way lowering the development cycle, and also higher quality because the test capability that can be implemented is at a higher level. And that's the spirit of the collaboration with VI-grade, and we're very excited for this partnership.
All right. Obviously, we've only got a limited amount of time here, and I'm more than happy to set up meetings with you one-on-one afterwards to go into a deep dive into some of the topics we touched on. But please, go ahead and ask some questions.